if you look at a conventional retaining wall, like this is actually shows a bridge abutment. So normally the codes specify within this we know it's the critical failure plane. So within this zone, we have to use a select fill. So normally this is the fill which applies earth pressure on this wall like that. So the coefficient of earth pressure depends on the friction angle of this soil. So normally we need a good quality soil with good friction angle and free draining material so that pore pressures don't develop. So same concept we have here, like this is the reinforced soil structure. So this part only determines how much tension comes onto the reinforcement. So we need the best quality material in this zone. So we call it reinforced fill. Then this is now our retaining wall. So this retains this soil. So again, this applies earth pressure on this block. So again, we need a reasonably good quality soil here. May not be as good as that, but still the property is important. So behind this zone, this has no effect on this wall actually. So this is normal soil can be used. So three zones like reinforced soil, retained soil. So this is general backfill. Again, foundation soil. That is. Now, which are the properties important like earth pressure? We know Ka is equal to 1 minus sin phi by 1 plus sin phi. So the friction angle is important. Then soil reinforcement bond, like the reinforcement has to develop good bond with the soil. So again, that is important. So ideally, there should not be any excess pore pressure. So it should be free draining. Then another aspect is insulation damage, because geosynthetics are polymeric materials. So we put in the soil, we place a layer of fill over that, then we compact with heavy rollers. So it may undergo some damage. So this is a function of the type of soil. Like if you have very coarse angular particles, it can damage more. Like that. Then another is durability of the reinforcement, because the reinforcement is sitting in this fill for 50 years, 100 years. So it may undergo some damage. If the fill is chemically aggressive, then it can go damage like that. So these are the properties which again the code specifies, which are, there are certain limits like that. So we have to use that. So different codes have given different specifications. So normally what's a good quality reinforced soil? One criteria is the fine should be less than 15%. So what we call a granular fill. So normally fines are more than that, then it is poorly draining, and it's more difficult to compact also. Coming to the retained fill, again in the design, the retained fill applies earth pressure on the reinforced soil block. So higher the friction angle, lower will be the earth pressure. Like that, it will be more economical. Again, we don't want pore pressures here. Like that. So again, these are the important properties. Again, the code specifies, different codes give the specifications for different soils. So that's the different components. Now coming to the design. Again, we have different codes actually. We have an IRC code, then which is more or less based on this British standard that we call BS 8006. Then there is a Federal Highway Administration Code. There is a NCMA, this is from the USA, National Concrete Masonry Association. This is only for segmental retaining walls. That means walls which use segmental blocks as the facing. This is the French code. Again, different countries have different codes. These are some of the most important. So normally the principles we learn from the textbooks actually, but the practical design is always done based on the codes of practice. Because this is important, because normally how do we formulate the codes? It's based on experience. See, first we design, construct the walls, gather experience, say 5 years, 10 years, 15 years, then we formulate the code. So these are based on the experience of large number of people, so we know what is important, what is not important, what is critical. So basically we have to follow the codes, and the code is what, see, normally we have what is known as a standard of care. Like if I am a doctor, there is a minimum standard I have to keep. Otherwise, I'll be liable. Like if, in case something goes wrong, I'm liable. So for us engineers, this is like a standard of care. In any country, the codes define what should be the standard of care. So as an engineer, if I follow these codes, I am safe actually. still it's not that it's going to be always safe. Sometimes things may go wrong, but as long as I follow the code, like nobody can find fault with me. And another thing is not that codes prescribe everything we have to do. No, like see, these are the most common things will be there, but many a time we face a problem for which answer is not in the code. So there basically we have to go with first principles and good practice. Again, the design philosophy, like we have like something known as limit state method, which is in the IRC, British, French code, they follow the limit state code. Then the US, like the Federal Highway Administration and AASHTO, they call it LRFD, load and resistance factor design. More or less similar like that. Because here what we do, like we have partial load factors, partial material factors like that. Then earlier approach used to be lumped factor safety, or what we call a working stress design type of thing. So the factor safety is like we don't have load factors, material factors, everything is lumped into one like that. So the NCMA still follows this lump. So gradually like people are moving towards the limit state like that. Because in structures, everybody follows limit state. Geotechnical, slowly we are moving to limit state design. Then just the load combinations, the BS, like see, there are different loads actually, and they don't act simultaneously. So there are different load combinations actually. So we have to evaluate various load combinations so that even in the most critical ones, the structure is safe. This shows like for a, with the walls, like normal retaining wall, like for the, if it is a bridge abutment, again there is a different set of partial factors. So just to give an example, like these are the partial load factors, then material factors, and safety factors. Like if you can, like if it is the friction angle, the material factor is 1. If it is undrained cohesion, material factor is 1. But if it is, if you are using effective cohesion, there is a 1.6. So that means we have to be much more conservative there, take a higher material factor. Then the partial factors of safety are specified. Now, if you go to AASHTO FHWA, they have a like a strength limit state, which is pertaining to the collapse limit state. Then there are extreme events, like one is earthquake. Earthquake doesn't happen every day like that. So once in a while it comes, so it's an extreme limit state. Then there is another like if it is a highway retaining wall, we know there is a crash barrier. So a vehicle comes and hits. So that is also, sometimes it happens like an extreme event case like that. Then serviceability like that. Then load factors are given like, then the resistance factors are given. So that means that first they will do the nominal loads, then multiply with the load factor, which is greater than 1. Then the resistance, for example, shear strength, they calculate, then multiply by the resistance factor is always less than 1. Then they evaluate what is known as a capacity demand ratio. Like capacity is this much, what is available, like demand is actually the load. So the ratio should be always greater than 1. Then your structure is safe like that. Coming to the basic mechanics, so we have the reinforced soil wall, that means reinforced fill plus reinforcement. So this is like a gravity wall now. So this is, this retains the retained fill. So this retained fill applies a pressure on this, trying to push it forward, overturn, plus this imposes loads on the foundation soil. See now, like in the process, first, like we have this reinforced soil wall, the reinforcement develop tension. Then we'll have to see that the tension, first of all, it is internally stable, like that, then only the wedge will be stable like that. So this stable as a stable coherent mass. Now this is acted upon by the retained fill. So as a block, this could fail, like sliding, overturning, like that. Plus, this imposes load on the foundation soil. So, bearing capacity failure, settlement, these kind of things like that. See, now coming to what are the steps in design? First, the data. We have to collect the basic data. Then what is known as preliminary sizing. Like, see, these are what you call a trial and error design. First, we have a preliminary cross section, then analyze whether it is safe. Then the collapse limit states, that means failure basically. Then the serviceability limit states, then detailing, like that. Now, what are the data for design? Like the wall height, like similarly loads and surcharges, especially if it is, there could be some dead load surcharge, traffic live load. Then if it is a bridge abutment, actually the bridge loads. Then like if it is a river, then scour, flooding, sudden drawdown, things like that. Then the material characteristics, reinforcement and facing, plus the reinforcement and fill foundation soil. Then here, this part is also very important. We have to do the geotechnical investigations up to the required depth. Then there could be like special functional or performance requirements, like a bridge abutment like that, or the wall is supporting a footing. Then coming to the preliminary sizing, there are three aspects, like mechanical height, then the minimum embedment, then the minimum length of reinforcement. See, now the mechanical height is actually applicable for some codes like IRC, PS and French codes. So this is actually the wall height or the facing height, but they define a mechanical height, like you draw this line and this angle is defined, and where it intersects, this becomes our mechanical height. Or here, common situation is this, like a highway retaining structure, like this is the parapet and this is the top of the pavement. So in this case, mechanical height is from the top of leveling pad to the top of the pavement. Whereas like NCMA or the FHWA, they don't have this concept of mechanical height. Now the embedment, that means how much should be the foundation below the ground level. So this is like any other foundation, like what are the factors, like bearing pressure, then the ground slope, scour and erosion. Then especially in a swelling soil, like we want the foundation to be below the zone of seasonal moisture change. And where we have, there should be temperature variations, I'm sorry. Like we have the problem of frost actually in cold climates. Like when the soil freezes, it swells, trying to lift the structure. So ideally our foundation should be below the zone of frost. Then future excavations, like suppose you construct the wall and somebody is come to dig, it should not be undercut like that. So again, codes specify what are the minimum embedment. Like normal common is like h/20. That is the minimum. Many codes specify that. And minimum, like if it is IRC, it says minimum 0.6 meter. But see, normally we have to go this. There is an order of precedence. Like if you are building a highway structure, like MOR, the MORTH specifications, for roads and bridges, that will have the highest priority. So anyway, we'll have to go for 1 meter, like the minimum. And like here, the British code minimum 450. Again, actually this comes from the frost condition, because in UK, the depth of frost penetration is 0.45 meters. So minimum that much we have to provide. Whereas NCMA, we can see like it's only 150 mm. Because these are all actually for private structures, like if you are like making a building somewhere, we want to do some landscaping. So here we can take some more risk actually. We don't need very deep excavation. So they allow up to 150 mm. So we have to decide which code we are designing. Accordingly, we'll have to provide. And these are the minimum. Like if you feel it has to be more, always we have to provide more. Then coming to the minimum length of reinforcement. Normally this is minimum is 0.7 times the height of the wall. That is the minimum. Like only NCMA, they give slightly less. So as I mentioned earlier, these are actually for private structures actually. So we can have little more risk so that we get economy. Whereas for transportation structures, minimum 0.7 times height or 3 meter. That means if it is a like a 2 meter high wall, 0.7 times height is 0.7 into 2 is 1.4. But still we'll have to provide this minimum 3 meter. We cannot have less than that. And again, this is on level ground actually. Suppose we have a slope in front of the wall, then it has to be more. And similarly, if it is a bridge abutment, it has to be more, like that. Then we come to the collapse limit states. So first is to ensure stability. That means wall should not collapse. So here, external stability. That means the failure happens outside the reinforced soil zone. That means here the strength of the reinforcement does not come into picture actually. So these are the different, and if you look at it, like it is exactly the same as for a conventional retaining wall, like a gravity or a Gaussian wall. These are the failure mechanisms which we analyze. So for reinforced soil walls also, same principles. So first is sliding along the base. Like we have this reinforced soil block. So now the retained fill applies active earth pressure on this block, which tends to push it forward. And I have compared like a cantilever retaining wall. Like suppose we have this cantilever retaining wall. See now, how do we analyze the sliding? Like this mass is considered part of the wall itself. There is a vertical force, there is a horizontal force, and resistance from the frictional resistance at the bottom, like that. So how do we calculate the factor of safety against sliding? That means what is the resistance? Basically friction into the length. That gives the resisting force. Of course, like if some cohesion is there, that can be added, but it is rare actually. Then the disturbing force is the active earth pressure, total active earth pressure. So this is actually a coefficient of friction into the vertical force divided by this is the factor of safety. And normally like 1.5 minimum has to be there. But of course, when we use limit state, it will be slightly different. Like there will be partial load factor, partial material factor, it will vary. Then see now, like if the factor of safety is not enough, what do we do? Like if it is here, either we can increase the length of the base slab. So it will increase the weight, it will increase the resistance, or we can go for a shear key. Like, but here, like we can, of course, there is no possibility of a shear key. So we have to basically increase the length of the reinforcement, or we can do some ground improvement that is possible. So what we normally do is minimum we have to have 0.7 times height. So first we'll analyze with 0.7 times height, see if it is stable. If the required factor safety is available, well and fine. But if it is not there, then we'll have to increase the length. Second is like bearing capacity. Now there is a vertical force, there is a horizontal force. So we have a trapezoidal distribution. So normally we have we ensure that the maximum bearing pressure is less than the safe bearing capacity. Or nowadays we go for this Meyerhof distribution, like we assume like whatever vertical force divided by L minus 2E. Again, that way. So normally structural engineers, they prefer this, normally they go for this type of distribution, but geotechnical engineers, we prefer the Meyerhof distribution. Okay. Same thing here also. Like, so the length of the base slab is equivalent to the length of reinforcement here. Otherwise, the calculations are more or less same. So now, like the trapezoidal, like if it is like a rigid structure, but this is flexible, perhaps this is more like this actually, the actual, this is from the BS code, the distribution will be here. Here, simply times it is gamma into height, that will be the pressure here. But here, because of this horizontal load, the pressure distribution will be somewhat like this. So now, this is the equivalent Meyerhof distribution. Like we take the RV is the resultant vertical force divided by B. B is the effective width of foundation, which is equal to L minus 2E. Same as like in our foundation design, we use this principle. And then we calculate we determine the bearing pressure. Then we can determine the bearing capacity, ultimate bearing capacity. So here our foundation width is also L minus 2E. So just like we calculate the bearing capacity of a foundation, like a strip footing, same way we calculate the ultimate bearing capacity. And again, we can have two cases like drained or undrained. If the foundation soil is a saturated clay or silt, short term we know the behavior is undrained. So we can use the relevant like untrained cohesion and untrained friction angle. So NC, N gamma, and NQ will become from the untrained friction angle. But if it is a granular material like a sand or a free draining, we can go for a drained. So this will be C will be C dash and friction angle will be phi dash. So bearing capacity factors will be based on phi dash. So this is the appropriate analysis we have to do. See now, like if you find the actual bearing pressure is more than the safe bearing capacity, what do we do? Like a normal footing, like if it is a column with the footing, what do? We provide a larger footing, increase the area of footing, then the bearing pressure comes down. But here, like we cannot do that actually, because if we increase the length of the footing, what happens? Our load also increases actually. So at best, like however much we increase the length, our bearing pressure this much will be remain, the gamma h like that. See, what will happen is our E can become 0. So beyond that, you cannot reduce actually. So there is a limit. Like by increasing the length, some factor safety can, some increase is possible, but not a large increase. So there again, we'll have to go for ground improvement. Then another is eccentricity. Like again, we are familiar, like when we are designing a masonry wall or a PCC wall, that middle third rule, like we have a vertical force, we have a horizontal force. So the resultant, where does it fall? Normally, in the case of a PCC wall or a masonry wall, it has no tensile resistance. So one requirement is, see, nowhere in the structure tension should develop. So that means as long as the resultant falls within the middle third for a rectangular section, we know tension will not develop actually. Another is the bearing pressure distribution here. Like one requirement is again, like if this goes outside, actually here theoretically tension will develop like this. That here it is compressive actually, but if eccentricity more, here can, of course, we know in the soil tension cannot develop. So our this bearing distribution will shift like this. So that means the foundation will be overstressed. So ideally we want a no tension condition. So resultant should be within the middle third. That was conventional. And how do we calculate the eccentricity? Like typically L by 2. This is the resisting moment, driving moment divided by this. That will give us the value of eccentricity. And earlier codes used to specify that resultant should be within the middle third. That means eccentricity should be less than L by 6. Another is conventional is overturning. Like any gravity wall, it has to be safe against overturning. But normally, like the reinforced soil, it's not like a rigid block. Like it's difficult to visualize like a soil mass overturning as a rigid body. So most of the codes now they have realized, okay, this is not relevant to reinforced soil walls. So here I have compared the various codal provisions. Like this is the different codes. Then whether check for overturning is required, whether check for eccentricity is required. Like if you look at IRC, it requires, it says it should be checked for overturning. Then it has specified E should be less than or equal to L by 6. Whereas BS, it does not specify, like overturning check is not required, neither does it put any limit on eccentricity. Coming to French code, same as BS. Then if you look at FHWA, like overturning check is not required, but it did put a limits on eccentricity. Like if you look at here, it is L by 4, like if the foundation is soil, then it is L by 4. But if it is the wall on rock, we can go up to 3L by 8. Similarly, NCMA, like overturning is required, but then eccentricity is not required like that. So different codes, like different specifications. Like now, only slight problem we have with IRC. See, this L by 6 was with the old days, like which was not a limit state method. That means we are load is not with the load factor, the actual typical working stress, that was okay. And if you look L by 6 there, but if you look at the FHWA, which is a limit state or LRFD design, so here the loads are factored. So there, if you look at E is less than L by 4. So now like if you design with IRC, see normally what happens, IRC basically it follows the BS, design is everything as same, but somehow those who drafted the code, they felt, okay, eccentricity is missing, I should put it. But now this can be like, what you call very conservative actually. So many cases you are like, if it is safe in everything, but just to satisfy this, we have to increase the reinforcement length. Whereas perhaps we could have gone for that actually. See, normally, like we did not realize at that time, okay, because see, I am putting a limit state design, so I cannot just pick up this from another design philosophy like that. So a little bit complicated like.